Hello and welcome to another video. I am Salar Khan. Today I want to talk about confidence intervals. Now, look, we want to set up the correct context for this. And it's important to recognize this first that when you work with a population, when you're trying to understand a population, when you study some population to understand a few things about it, perhaps, you end up with what's called as sampling. So you basically look into some samples from this population, and you expect that these samples are going to be a fair and a credible representation of the population. Why? Because you do not have access to the entire population, right? It's why you do sampling. It's why you take a representative chunk from this population and you say that this is going to be a fair, credible, solid representation of the population. Now, you could look into any metric, but let's talk about one, the sample means. Say we're working with some study on height of people in a city. Now, you might not have access to everyone in the city, but you could always sample out a few people to get a good representation. Now, you take an average of their heights and you come across what's called as a sample mean. And you hope that this sample mean is a good and a solid representation of the population mean. So you want sample mean to be a fair, credible representation of the population mean. You want it to be a good estimate. Now, it'd be fair if we go ahead and compute this average and, say come across a number 73 inches, talking about heights, as one number. And we could always report this one number. But what really happens, and in most studies also, and especially in research studies, you end up with what's called as some margin of error, so to speak. Now, so this is 73, and there's plus minus 5. Well, these are just example numbers. What this really does is it says 73, and you could go 5 up, make it 78, or you could go 5 down, make it 68. So essentially, what's really happened here is instead of just one number, one sample mean reported, what you really can do is suggest an interval, such as this. You know, so what this really does is it brings in more confidence to what you are reporting. It brings in, say, more belief in what you're reporting. Now, instead of saying that there's a sample, there's a mean value, you could rather associate an interval with this mean value and say the population mean is estimated to be between this interval. And this makes your claim to be more credible because instead of just one number, now you've specified a range. And not only that, what we really do is we also assign what's called as a uh, percentage, a confidence percentage with it as well, right? So what we really do is then specify an interval and we associate a percentage. That look, we are 90% confident that our estimate of the population mean is in this um, interval, and the population mean actually resides in this interval, right? And we are 90% confident about it. Now, this happens in a lot of researches. It's done with a lot of values, not just the mean or the sample mean. In this case, there's some coefficient. They've reported a confidence interval here too, right? So they report an upper and a lower value. So, point here being, it's always better to report a number, but then also the upper and the lower bounds of this and associate a percentage of your confidence with it. Now, how can we interpret this? What does this really mean? What does it mean that you're confident 90% about this interval? Now, what that really means is, if you consider average height of students in a class is between 71.3 and 74.8 inches, the confidence of 100%, what does this 100% confidence mean? What it really means is that if you took sample means 100 times, all 100 out of 100 times, the sample means is going to be within this range, within this interval. This is what it means. This is what 100% confidence means. A 90% confidence would mean that 90 out of 100 sample means are within this range. Now let's visualize this. What I've done here is I've gone ahead to plot all 100 sample means. Each vertical line that you see is an interval. This is the upper bound, this is the lower bound, and the center point is the average. So you see three numbers: upper bound, average, lower bound, and then there are 100 such vertical lines. The averages are connected with these dotted black lines. Now, you can see these 100 experiments, 100 sample means, 100 upper bounds, 100 lower bounds, and then there's a red line, which is the population mean. So it's as if to say the population mean fits within all 100 intervals. That's why I'm confident, I'm 100% confident that the estimates that I'm getting from sample mean are well, you know, they're well set up for these intervals, which is 71.3, somewhere around here, 71.3, and 74.8 is somewhere around here. So within these range, within this range, 71.3 and 74.8, within this range, I'm 100% confident that my population mean resides, because all 100 sample mean ranges encapsulate this population mean. So that's the intuitive sense of what a percentage or confidence percentage really is. Now, let's kind of lock down how we could show it in the form of an equation. This is what an equation looks like. This is confidence interval. You report a sample mean value, and then you add and subtract a factor to it, right? So there's a sample mean value, and then you're adding a factor to it. Notice there's x bar plus z, s over under root n, and then you subtract from this x bar minus the same factor, right? So you arrive at the lower bound. So there's an upper bound and a lower bound. Add the factor for an upper bound, subtract the factor for the lower bound. S is the sample standard deviation, and is the number of samples that you consider, and z here is a z-score. Now notice that we've talked about something being 90% or 100% confident. So you've got to factor in that confidence here in this equation somehow, and it happens through the z-score. Now remember, when we talk about the normal distribution, we've talked about normal distribution extensively. Now when we are saying that we are 90% confident about something, what we really saying is that the 90% of the content is right here. Probability of number falling, right, is 90% around here within this range. Okay, and then this then means that you need to lock in a corresponding z value, and since this is symmetric around center, whatever z that you see here is the same as here, so that would be minus z, just negative, because the center is at 0. So when you talk about a 90% confidence percentage, you're essentially wanting the data or the sample means to lie within the central 90%. Now, if the center is 90%, then since this is a symmetric normal curve, the remaining 10% is distributed on either side. Right? It's 5% here and 5 here. That makes it 100%. 90 in the center, 5 on either side. Now, what you need to understand at this point is, when I'm looking for this z value, what the z table or Excel usually gives us is the entire area to the left hand side of the z value. Now, the entire area to the left hand side of the z value is this. It might take a few seconds to show up. Yeah, so it's this entire red region to the left of z value. That's what the Excel formula does. It gives us the entire region to the left hand side of this z value that we put in. So what is that entire area? That entire area is no more than 90, it's this 5% also. So it's 95%. So in order to get this z value, what I would really need to do is reach out to Excel and plug in what's called as the 95.95 area to get this z value. And that is something that I could then use to plug into this formula right here and calculate my confidence intervals. Let's go ahead and do this as an example and sort this out. So I'm going to go ahead and look into some sample values. I already have a bunch of sample values here listed for me. I have sampled out these 5 values. One of the things I would right away need would be an average, right? So average of what? Average of these. I'm holding the shift key and then clicking the last one. Close the brackets. I've got my average. Now, in this average, sample mean, I'm going to add a factor. For the factor, I need these 3 components. Let's go ahead and get them one by one. First one is a standard dev, then there are a number of values that are 5, and then there's a z-value. We'll get to z-value again. Let's go ahead and get the sample standard deviation, stdev.s for sample of these 5 values, close brackets. I've got the sample standard dev. And then there's a z-score value now, which I need. Now the z-score value has to come in based on the area that we have set in. Now, what we have is got probabilities, right? And I'm gonna use the inverse formula. I'm gonna use the standard normal inverse formula because we are working with the z values and it needs me to add the probability to it. Now I'm going to add 0.95. Why am I adding 0.95 is because this z value corresponds to 0.95 area. For a question that needs confidence of 90%. So for study, for question, anything, for confidence interval that needs a 90% confidence, I need to plug in a z value corresponding to 95. So you plug in 95 probability, you get a corresponding z-score. I'm going to use this z-score now to calculate this factor. Now, what is this factor? Let's go ahead and talk about this factor. This factor is going to multiply. Let's write this one more time. This factor is going to multiply my z value with what? It's going to multiply my z value with the standard deviation, right? Z value with standard deviation and then divided by square root of n. And then divided by sqrt square root of n. Now I know there are 5 values, so I can do that, but I will go ahead and put brackets, make sure everything looks good. These two get multiplied within the brackets, then your answer gets divided by the square root of 5. Hit enter, and I got my complete factor, right? That's the margin of error, so to speak. It encapsulates what? It encapsulates z times the standard error. Okay, so another way to see it is um, you're moving standard error, and this is the standard error of the mean, but you're weighting it. You're adding some weight to it by z, which is essentially your confidence. So how much of standard error, how much of standard error of the mean are you adding to the mean value? So that is what is making an interval right here. So again, this is the sample mean. Here is where we add to it, right? So this factor we add. Let's do it one more time. Actually, I might as well just reduce this a little bit so I could, yep, I could access the cell correctly. Let's break it down a little bit more. Okay, yeah. Okay, now let's go to this. So I'm going to add to this our factor, and then over here I'm going to subtract from it our factor, right? So we've got these 3 values. The mean, this is the sample mean. Then we have the lower bound, and then this is the upper bound, right? So we've added the factor and subtracted the factor to the mean value. We've got upper bound and the lower bounds. So we've got our confidence interval now. It is from 72.44 to 74.36. Well, that's about confidence interval. The key takeaway really is computing sample mean values and then adding to it a weighted standard error, which is weighted by the z value. The z value or the z score is coming from the confidence percentage, which we set on our own. So if we want this to be a strict confidence percentage, perhaps let's just set it to, just for the sake of let's just set it to another, say, I'm going to intentionally use a decimal value to make it a point. We could set it to anything, maybe set it to 98.6%. If you want to be 98.6% confident, then what that means is the central 98.6% is encapsulated here, and the remaining 1.4 is going to be distributed on either side. So 1.4 on either side would mean 0.7% here and 0.7% here, right? So 98.6 plus 1.4 equals 100. Okay, so this completes the 100. And I'm more looking for this z value, right? To obtain this z value, I am going to, because Excel takes the entire area to the left hand side of this, it means 98.6 plus zero point 0.7. Both of these would be needed to find the inverse probability, right? To obtain this z value. And 98.6 plus zero point 0.7 is just going to be 99.3%, right? So what I'm going to be putting in my inverse formula is 0.993, and it's going to give me a z value, which is actually going to be this z value. Okay, so let's just go ahead and change the confidence percentage just a little bit, 0.993. Since we have the formulas already logged in, or well, you should update accordingly. So if um, actually, before I do, let me copy these and paste them here as numbers. Can I paste them as values, right? So I'll have the original values with me, and I'm going to change the confidence just to go, make it a stricter confidence. Instead of 90, if I want to be more strict on my confidence, just want to see what happens to the bounds. So 0.993. Also, just let's just say this is for 90%, and this is for 98.6%. Okay. Uh, yeah, 0.993 was supposed to go in here. Yeah, 0.993. There we go. These are our updated bounds for 98.6%. I'm gonna put them here for comparison, and might as well just increase there. Yeah, it's a percentage. Okay, so there we are. Notice what happens. Uh, Obviously, sample mean remains the same, but the lower bound has kind of widened, upper bound has widened as well. So what's really happened, if you could, I'll just bring this over there so I could annotate this. It makes up for an interesting conversation. Yeah. So I'll just give this a second. Yeah, so there you are. So you see, what's really happened is when you had a 90% confidence on your sample mean interval, you had 74.3 and 72.4. You had this range, okay? You had this range, so to speak. But once you increased your confidence percentage, what really happened was the mean is at the same level. You could see these values are still the same, but there's a slight change in the upper and lower bounds. And if you notice closely, the upper bound increased further, and the lower bound decreased further, right? So it became something like this. And and now, if you notice, why should you have more confidence on a higher interval? Well, technically you should, because you're reporting a bit wider range now, and there are more chances that the population mean is within that wider range, right? It's within that wider interval. So if it's within that wider interval, then you should be more confident. It's as if saying, the average height in a city is going to be between 0 meters and 0 inches and 100 inches. 100 inches is over what, 8 feet. So you don't see people above 8 feet. So you're 100% confident. But as you narrow the range down, you end up losing that confidence because now you have to be super strict about it. So making an estimate on population mean uh, comes with a certain confidence percentage, which is obviously tied to the confidence interval that you're reporting. And in this case, we've seen as we increased confidence percentage, we wanted to be more confident about our estimate. The upper and the lower bounds widened, they brought in a higher confidence interval. Happy to answer any questions in the comments. Thank you so much. I'll see you in the next one.